Hello everyone and welcome to this lecture. In this lecture, we will start with a easy bound on largest eigenvalue of graph in terms of its number of vertices and number of the edges. Okay, and then we will start the theory of the largest eigenvalue and the corresponding eigenvectors for a non-negative symmetric matrix. Actually, this theory was given by two mathematicians Perron and Frobenius more than 100 years before, but we will restrict the our discussion, and this theory was about the non-negative matrices, but we will restrict the discussion and the proofs and everything only to non-negative symmetric matrices, because we have to use only the symmetric matrices for our course. Okay, so let us first start with a bound on the largest eigenvalue in terms of the number of vertices and number of edges. Okay, so let us start. Yeah, so it says that suppose in a graph G there are n vertices and m edges. Okay, then the largest eigenvalue, lambda 1 is always less or equal to square root of 2m n minus 1 divided by n. Okay, yeah, so how to prove it? How to basically by knowing by knowing the number of vertices and knowing the number of edges, you can tell what will be the most what can be the value of the lambda 1 at most. Okay, so let us prove it. Okay, again we will try with some help from a spectral theorem. Okay, so one thing is that we know that the eigenvalue sum if you sum all the eigenvalues, okay, so this is equal to 0 because this is trace, right? So one thing is sure. Okay, and this actually gives that, because we have to write in terms of lambda 1, so better to keep it separate. So lambda 1 equal to minus of all these, right? Minus of sum of I equal to 2 to n, then lambda h, which essentially means that this guy is less or equal to sum of mod I equal to 2 to n. Very simple fact. Okay, so let me write it 1. Okay, another thing is, again from the spectral theorem we can find that sum of square of these eigenvalues, okay, will be equal to what? Will be equal to twice the number of edges. Yeah, and which in terms means that this implies that, again I will separate lambda 1 out, so this is 2m minus sum of I equal to 2 to n, and then square of these, right? Yeah, so lambda I square. Okay, so let us call it 2. Okay, so these two facts, and can we prove it only these two facts? Maybe yes. Okay, yeah, and next let me define a vector which is actually only consists of mod of values lambda 2 to lambda n. So basically lambda 2 mod lambda 2, then mod lambda 3 up to mod lambda n. Okay, so, and I will call it transpose because I am always, when I mean a vector, that means a column vector, so it's good to denote it by y transpose. Very good. And there is, suppose, one more vector, all one vector of dimension n minus 1. Let me again do this. So this is all one vector, and using these two vectors we will prove this inequality. But before that, I need to use a famous inequality that we call Cauchy-Schwarz inequality. So let me write it as here. So Cauchy Schwarz. I hope I write the spelling Schwarz. Okay, Schwarz. Maybe this is the correct. Anyway, please check Schwarz. Please check the spelling. Okay, inequality. Okay, it means this. Suppose you have two vectors x and y. Okay, so you take dot product of vector x with itself and multiply with the dot product of y with itself. Okay, this quantity is always greater or equal to if you take dot product of x and y and then a square. Okay, very famous inequality. Okay, so how to make use? So let us do this, make use of this inequality for these two vectors. So this will give you what? Y transpose y times 1 transpose. So I am not writing this n minus 1. So this will give you, so this is what? This is, yeah, so summation over yeah, you are multiplying basically with the same things of y I a square. So this is nothing but this, right? I equal to 2 to n and then times n minus 1 and this quantity has to be greater or equal to, if you dot product this is y transpose 1 and then you take a square, which means this. So which means what? You are multiplying with this and then yeah, each and then taking a square. So basically you are summing all this and then taking the square. So basically sum of lambda i's where I equal to 2 to n and then you are taking a square, right? But hold on, can I write this quantity as something else? I hope, yeah. So we know that this quantity is greater than lambda 1. So this quantity is nothing but greater or equal to lambda 1 square. Up to where it is correct, up to where it is clear. Now again, can I write this quantity in terms of number of edges and number of vertices? Then I think the inequality will be apparent, and fortunately yes. So you can write this quantity as lambda 1 square, this is lambda 1 square minus 2m, no, 2m minus lambda square. So this quantity is nothing but 2m. Remember, these are mods and they are squared, so it doesn't matter. So basically this, so 2m minus lambda 1 square, right? This quantity times n minus 1 is always greater than lambda 1 square. Now I hope this inequality will follow. Yeah, so let me write this. Yeah, and what I have to write in terms of lambda 1. So yeah, so let me open it. Wait, so this will be equal to 2m minus lambda 1 square greater or equal to lambda 1 square divided by n minus 1, and then I can take n lambda 1 on that side. So further means greater or equal to lambda 1 n minus 1. So basic stuff. Yeah, equal to lambda 1 square, then 1 minus plus 1. Now it is clear. Yeah, so this is indeed equal to lambda 1 square. You add this, so this n divided by n minus 1. Okay, and then it is clear, right? So this is, so this implies that 2m times n minus 1 divided by n, and then you take a square root, will be always greater than lambda 1. So we are taking only the plus case. Yeah, okay, so this we have proven. Okay, so very simple one, and you just check for which kind of graph this is actually the equality. Okay, so when for which type of graph the equality holds. Okay, now let us move to something more interesting, and this tells you about more nature of the largest eigenvalue and largest eigenvector. And this is actually this is a consequence of very famous Perron and Frobenius theorem on non-negative matrices. Okay, so Perron-Frobenius Frobenius theorem and theorem, but specialized for our case, right? Specialized for symmetric matrices, non-negative, in fact, non-negative symmetric matrices. So I have non-negative, like adjacency matrix, okay, non-negative. Okay, so I will not be stating what is the result in general case, but we have to only focus on symmetric non-negative matrices. So, and there are many consequences of this beautiful theorem, and then so I think I will cover in 2 lectures, at least 1.5 lecture. So today I will be starting, and the next lecture I will be completing this. Okay, so first thing is to see this. The first, let G be a graph, okay, or may not be. I mean, let me write it in terms of something. Let M be a non-negative symmetric matrix of order n or n cross n, okay. It says that then there always exists an non-negative eigenvector corresponding to the largest eigenvalue of M. It means that if M is non-negative, means all the entries are non-negative, means either 0 or positive, right? Then there exists a non-negative vector, again the vector which is only either 0 or positive entries, and this eigenvector is corresponding to the largest eigenvalue of M. Okay, so very neat fact, beautiful fact. Let us prove it. Okay, prove it. Okay, so suppose lambda 1 is the largest eigenvalue of M, so basically and there is a corresponding eigenvector x. So okay, so maybe so let me write in place of x v. Okay, that will be more actually suited here. Okay, so v is eigenvector corresponding to the largest eigenvalue, and v you assume to be normalized one. Okay, unit vector. Now suppose x is nothing but x is a vector which is mod v. Mod v means whatever the entries in v are, you take mod of this, absolute value of this. Okay, so we know that, right? So from here, if you see that, so v transpose mv will give you what? This will be indeed giving you lambda 1, right? And this quantity is always less or equal to this quantity x transpose ax. Why this is true? Because in x every entry is positive or non-negative, a is also non-negative. Okay, so that's why this follows. A is non-negative and x is also non-negative, right? So that's why this quantity follows. Okay, now if you see carefully, your lambda 1 is always greater than this. We have seen this earlier, right? I think 1 or 2 lectures before. Lambda 1 is always greater or equal to this quantity x transpose ax over all possible x. But since we know that lambda 1 and lambda 1, I mean both sides there are equality, right? So I mean everywhere there has to be equality. That means lambda 1 is indeed equal to x transpose ax. And we have also proven that if this happens, then this actually implies that this happens for the largest eigenvalue. So this implies that x is an eigenvector corresponding to the largest eigenvalue. This also we have proven, right? So x is also an eigenvector. Okay, so and x is x is a non-negative eigenvector. So there always exists a non-negative eigenvector. Okay, very good. So very neat fact. Okay, don't take such things as obvious one. They are very small thing, but it will be very useful in proving many other interesting results. Okay, so let us move at for another nice result, which is about the connectivity of graph. Okay, so the result is this. Let G be a graph on n nodes or vertices. Okay, let x be a non-negative eigenvector, non-negative I don't know, I mean my grammar is not that great. Let x be a non-negative eigenvector corresponding to the largest eigenvalue of G basically adjacency matrix. We are talking about adjacency matrix. Eigenvalue, let me write it, I mean otherwise you may be confused. Corresponding to the largest eigenvalue of the adjacency matrix of G. Okay, if there exists a zero entry in X, then G is disconnected. Very useful just by looking at the x, which is a non-negative eigenvector. Remember, due to the previous result or theorem, we know that there always exists a non-negative eigenvector, right? And if in this non-negative eigenvector, if there are some entries which are zero, this will imply that the graph is disconnected. How to prove this? Okay, so let us go to the proof of it. Proof. By the way, you can always pause this. And think about these questions and then see the proof later on. Okay, very good. So yeah, so how to prove this? Okay, now yeah, so basically it says that suppose AG is the adjacency matrix of my graph G. Okay, and it tells that x is equal to lambda 1 x. Lambda 1 is the largest eigenvalue. Okay, now let us make two group of vertices. Okay, so it says that in X, if there are some zeros, let us consider there are some zeros. Okay, so let us make two group of vertices. So one group is H group. So H consists of all the vertices. So set of vertices or set of V. I would set of vertices such that X V, or I mean suppose you are naming the vertices as, maybe more correctly naming the vertices as 1, 2. So suppose your vertex set is this up to n, and rather than B, now I will then make use of this, right? Suppose this consists of all the vertices I such that xi is equal to 0. Okay, and then so these are the vertices. Rest of the vertices is basically this set of vertices I such that xi is greater than 0 because this is a non-negative vector, right? Okay, I hope. So xi is actually the ith component of this. So xi is the ith entry of x. Okay, very good. Now remember that x is non-empty, h is non-empty. Non-empty. Why? Because of given, right? Because there are we are assuming that there are some zeros, right? So h is non-empty, and also v minus h is also, and v minus h is also non-empty. Why this is true? Empty. This is non-empty because the eigenvectors by default are non-zero. Not all the entries can be 0. Okay, so this is also non-empty. Very good. Now claim is this. Claim. There cannot be any edge between h and v minus h. Why? Suppose, let us prove it using contradiction. Suppose I belongs to h and j belongs to v minus h, and there is an edge. Okay, so what will happen? In this case? So there is an edge between vertex I and j. Okay, so if you see carefully here by the definition here, so what will be actually your xi entry here? So basically, if I can write this as, so lambda 1, if you see xi is nothing but is equal to, it's just like you are multiplying the ith row of A to all the to the x, right? So basically it tells this. So this is nothing but summation over ith row of A. So suppose A is the entry of A is, so I am writing the generalized entry of A is Aij. Okay, so basically it tells that Ai, okay, and then what? Aik, suppose, where k equal to 1 to n, and then xk. This is just matrix product, right? So ith row of A will tell you this AI1, AI2, AI3 and so on, and you multiplying the corresponding entries in xi. Okay, but among those xk, right, there is also xj, right? J is also sitting over here somewhere because j has an edge, right? So this quantity, if you see that this quantity is always greater or equal to, so let me first write this, is equal to this, right? So summation over, again if you write k equal to 1 to n, right, and again ai k xk, and suppose in that case k is not equal to j, okay, and then you are adding xj here, right? This is same thing as you are broken into two parts, right? Now if you see, and by the way, this xi quantity is what? This xi is nothing because I belongs to h, and xi, every vertex in h are having this xi 0, so this quantity is equal to 0, right? Now what about this? xj is always positive. Xj is always positive because j belongs to v minus h, so this quantity is actually greater than 0. And this quantity is always greater or equal to 0, but this quantity is 100% more than 0 because of this. Now this is, if you see that, this implies that 0 greater or equal to 0, a contradiction. Hence there cannot be an edge between h and v minus h. And so if there are 0 entries, okay, so if there are 0 entries, this implies that graph is disconnected. Okay, so this implies that So zero entry in X implies that G is disconnected. Very good. I hope you follow this proof. Very simple proof. Okay. Now, I mean, these small proofs, crisp proofs, we will be utilizing a lot during our course. Okay. And okay, so I am stopping this lecture here, and the next lecture we will see more actually results on symmetric non-negative matrix, which will be highly useful for us. Okay, so till then, thank you very much and see you in the next lecture.